All right, so vectors, they're easy to work with because they follow these three rules. You can look at them one by one. Commutative. All of these, essentially what it means is that the order doesn't matter. When you're adding or subtracting vectors. So for the first one, a plus b is equals to b plus a. Would you agree with that statement?
Yes.
Yeah. So it doesn't matter which way you add first, the final answer will always be the same. Just give me 1 second. I am looking for my pen. All right, I found it. So just to give you an example of the first rule there, of course it doesn't work. What I'm going to do is I'm going to sketch vector A and vector B, and we're going to add them in a different order and see if we get the same result. This didn't work either. Okay, I know why it didn't work. It's because my tablet isn't connected to USB-C. Right now it should work. Yeah, there we go. Cool. So just to give you an example of part A, let's say this is A going this way, and let's say this is B going this way. Right now you can't add them because they're not tip to tail. So let's say we move B down here. Remember, you can move vectors around. So I'm just going to move B right here. Now that's my B, right? To add vectors, you go from tip to tail. Tip of the first vector has to be touching the tail of the next vector. And then you go from the starting point of the first vector to the ending point of the second vector, right there. So that is A plus B, the one in green. Yeah, you agree with us? Now, in the same vein, our things look like this. This was A, this was B. I'm going to move this guy up there. You're allowed to move A up there. So if we do that, so this is B, this is A, this was A here. I moved this up top. Now I join again from the beginning of the first vector to the end of the second vector. And this is A plus B. This and B plus, sorry, that one is B plus A, the one I just drew. This is B plus A. This is A plus B. But the important thing is that they both represent this vector, which are equal. Okay, they have the same magnitude and they also have the same direction. So the order doesn't matter. 2 and 3 is the same thing, honestly. 2 is they put the brackets on the wrong end. They put a bracket here first and then they put a bracket here. A quick example would be, let's say this is A, let's say this is B, and let's say this is C. Let's go in a different direction. Let's say this is C. So the first method, it says add A plus B first. So if you were to add A plus B, you would get this vector going northeast like this. This is A plus B. The starting point of A to the ending point of B. And to this, we add C. And this would be the final answer right here. This will be the final answer. So that is doing A plus B plus C, but we can do this way as well. Let's add B plus C first. So this is B, this is C. Now that is B plus C. And we're going to be adding B plus C to A. So A is going this way. B plus C is going this way. Now if you connect them, you will get something like this. If I were to do this using a protector and whatnot, it'll look exactly identical, but I'm just eyeballing it here. But that right there, this, and this, they are the same vectors. The order doesn't matter. Same thing with a scalar multiple. You can open the brackets. This times this, you can also rewrite that as KB plus KA. There's no arrow on top of K because K is not a vector. K is just a constant, also known as a scalar. Yeah? So vectors, you can switch them around, makes them easier to work with. Let's do a very simple question here. This is just algebra, grade 10 level algebra. It looks weird, but you're just collecting like terms essentially. So let's start with this one. Let's open the brackets. 3 times 2, 6a. 3 times b, 3b. 3 times c, 3c. Minus. What happens to the signs inside when I open this bracket?
They switch.
Yeah, everything flips. So this will be a, that'll be negative 3b. This will be positive 2c, like that. And now you collect your like terms, 6a minus a, 5a. 3b and 3b gone, bye-bye. And then finally c plus c, 5c, final answer. That make sense?
Mm-hmm.
So we're just collecting like terms. There, you can just treat them as polynomials. Very simple. Do they want us to draw these? No, they don't want us to draw them. They just want us to do them. Oh, but now they have it in terms of I, J, and K. Alrighty, so I'm just gonna introduce you to I, J, and K. So now we're looking at vectors in R3. R3 means 3 dimensions. Last time it was X and Y, we're just looking at a plane. Now we're looking at a cube. So we're in R3, we're in 3 dimensions. In 3 dimensions, you can draw a grid like this. I'm going to use straight lines and dotted lines. So this is the positive Z or Z axis. This is the positive Y axis. This is the positive X axis. And then behind them, you have the negatives. You can visualize this as well. So I'm looking at my right hand. I'm going to point my thumb up into the ceiling. And I'm going to point my index finger towards the computer screen. And I'm going to extend out my middle finger. And the other 2 fingers are tucked in. It's a beautiful hand. So you can do this as well. Do it with me. Your thumb is pointing towards the ceiling. Your index finger is pointing towards the screen. And your middle finger is pointing sideways. Right now it's pointing towards the left. This is your z-axis. Your thumb is your z-axis. Your index finger is your y-axis. And your middle finger is your x-axis. Okay?
Mm-hmm.
This is called I. This is called J. This is called K. So let me sketch what 3i minus 4j plus k is. 3i means it's 3 units on the x. So we are here. 1, 2, 3. Let's say that's positive 3. Negative 4 means we're going 4 units in the negative direction on the y. So 1, 2, 3, 4. That's negative 4. So we start here, 3i. We're going to add negative 4j, so we end up there. And plus k means 1 unit on the z-axis there. Okay, there. So where does that bring us? Here. Cool?
Mm-hmm.
3, 4, and negative 1. When you combine them, you would get like a coordinate. Let me see if I can draw a box here. Okay, I think I can draw it right here. All right. So check this out. This is 3, that's 4. This kind of forms a rectangle on the XY plane. So this is just horizontal. It's flat, it's on the XY point. What we do is we take this vertex and I'm going to move this 1 unit in the Z direction. You see this? It's obviously going to be super hard to draw, but I'm going to take this plane and I'm going to lift it 1 unit up. So this point will come somewhere here. And that point, the coordinate of this point is going to be 3, -4, and 1. There we go. So that's the coordinate of this point. So what does this mean then? What does this mean? That is a way for you, okay? It's basically a path. You can think of it as a path to get to this point from the origin. So if someone asked you, how would you go from the origin to this point, then you would have to take this path. Again, the order doesn't matter. You can go K first, IJ later, okay? So that's what it is. And you can visualize it using your right-hand rule. Did you do this in physics? Probably not. You will do this if you talk about eventually when you're doing circuits, when you're talking about currents, voltages, and whatnot, you will see this exact same thing. Okay? Cool. In the physics context, your Z is your current, and your middle finger, that's the most important part, is going to be your force. J is the wire, the direction of the wire. So you'll be talking about these in physics eventually. We're not too concerned with those things right now. So that's the idea behind these. I made it a little bit more complicated than it needed to be because these questions are super simple. All you're doing is you're collecting like terms. I'm just going to do the first one. So look at this. X plus y, we have 3i minus 4j plus k. We're adding x with y, so y is j minus 5k. Now you just collect like terms. There's only one I, so 3i. 4i plus j is what? How many j's? We have -4j plus j. So how many j's are we left with?
-3j.
Yeah, -3j. And then finally we have k minus 5k, that's -4k. Put your arrows to indicate that they're vectors, and there we go. That's the answer to A. B and C is the same thing, yeah? You just multiply y first, here multiply z first, you correct like term. This is grade 10 level stuff. It's not too complicated. Okay, let's do this one. Yeah, I don't think it's that hard because we did this before with parallelogram. We just have a little bit of a 5-sided diagram. Shouldn't change anything. So we need to show that PQ is RQ plus SR. All right, where is RQ? This is RQ going this way. Direction matters, remember that. SR is this going this way. So if you add SR with RQ, what do you get? What is RQ plus SR, or SR plus RQ? What vector do you get? When you're adding vectors, the resultant vector is going to be the one that takes you from the beginning of the first vector, right, to the end of the second vector, tip to tail. Yeah? So RQ plus SR, when you add these two vectors, like in order doesn't matter, you can do SR plus RQ, that will give you the vector SQ. So that's the first part. The second part, TS plus PT. TS plus PT. So we're adding this TS and this. What do you get? This plus this. What's the resultant vector?
PS.
PS, yeah. PS, which will be this one. It goes from P to S. Now finally, when you add PS and SQ, what do you get?
PQ.
PQ, exactly. And that's what this is. So we proved the first one, right? Like that. Second and third is the same thing. I can do them. It's not that difficult. Again, do the things in brackets because BEDMAS never fails. Doesn't matter what we're dealing with, BEDMAS always applies. So here we have to do the bracket first. SR plus TS. SR is here, TS is here. What do you get when you add them up? SR is going this way, TS is going this way. So when you add them up, what's the resultant vector?
TR.
It is TR. So we're adding RQ plus TR plus PT. So TR is this. We goes from here to here. So I'm gonna first add PT and TR because I can already visualize it right here. PT plus TR is PR, yeah?
Mm-hmm.
These two is PR. And now we're adding RQ with PR. What do we get?
PQ.
Yeah, exactly. We get PQ again, which is the second sentence. And third one is the same. Actually, I'll give you a shortcut for this. If you're adding letters like these, and if there's a letter that they share, what do I mean by these? I mean, you have TR plus RQ, right? You see like this?
Mm-hmm.
These two disappear. TQ. I can prove it here. TR is this. RQ is this. From if you do the tip to tail rule, you got to start from the beginning of the first vector and the end of the second vector. You can see you get TQ, but you don't have to draw it out if you don't want to. As you can see, you get TQ here as well. The middle letter gets eaten up, okay? That's a quick way to do this. We can use that logic to do part C there. It just has to be arranged in the right form. So SR plus RQ, the middle letter disappears. That's going to be SQ. TS plus PT is not in the right form, but we can do PT plus TS. Make sure that these letters are the same, and it'll completely disappear. So that'll be PS, yeah?
Mm-hmm.
And then finally, we got to have the S's together. So we do PS plus SQ. This is the only way it's going to work. And as you can see, the S's disappear and you'll get PQ. So there you go. That's the algebraic way of doing it if you don't want to draw it out. The middle letter kind of gets eaten up. All right, so we have a rectangular prism, which is a 3D box. Part A, write a single vector that is equivalent to these four. So we can either do it from the diagram or we can do it using the letter disappearing rule. Both of them will give you the same answer. So let me show you. Let's do it the easy way first, which is the letter disappearing rule. So EG plus GH, what do these two combine to become?
EH.
So that's EH, and we're gonna add this with HC, right? The second one is HC. What does that add up to?
EC.
Yeah, EC. Well, let's see if that's true. I mean, it should be true. So we have EG. Where's EG? So we have this vector. We're adding to this GH. So we're adding this to it. To that, we're adding HD. So we're going up. And then to this, we're adding DC, right? We're adding DC to this. So we're going this way. But we know with vectors, doesn't matter how many of them we're adding, the resultant vector, the final vector, if you have it in the right orientation, as we do here, tip to tail for all of them, the resultant vector will always be the one that begins with the first vector and it ends with the last vector in this direction, EC. Yeah?
Mm-hmm.
And that's it, that's the answer. We got this using the algebraic way. We can also always draw it out like we did here. Part B. write a vector that is equivalent to EG plus GD plus DE. Super simple. EG plus GD is what?
ED.
That's ED. Plus DE. Now that D disappears, so you get EE. What is that? Doesn't make much sense, does it? Now we're going to do the same thing down here. Let's see where we end up. EG. So we have this vector going this way. To this, we add GD. So we add this. To that, we add DE. Yeah? What do we get? Think about it this way. What's your total displacement? You know what displacement means? Net change in position. We started here. We ended up here, right? What other vector could do this? What can we add to the point E so that we end up at the exact same point? We can add the 0 vector, yeah? Because there was no change of position, basically they did a full loop. Another way to get right back up here, this is the first path you can take. This one will bring you right back. The other path that you can take is just add the 0 vector. You'll end up right where you started, yeah? So that'll be the answer to that one. You can always add 0 vector, and then you'll end up right where you started, because 0 vector doesn't do anything. Part C, is it true that HB is GA? All right, so let's conjure up HB. To get HB, I'm gonna go up first. We go HD, and then I'm gonna go right. There's multiple ways you can take. So I went here, I went here. What's the last vector I need to add to this to get HB? CB. Yeah? We want HB. To get HB, I went up, across, down. There's other ways you can do this as well. That's just the one of the paths that you could have taken. What about for GA? Now we're gonna try and follow the same route. We're gonna go up first. So where is GA? GA is this way. So I'm gonna go up first. So that's GC. And then I took this path. I'm gonna go down next, CB, CB. So they have that in common. And then I go this way, BA, BA. Now, what does the modulus symbol imply?
It's the magnitude.
It's the magnitude. CB has to be equal to CB, so you don't even have to check these. Is DC and BA the same thing in terms of their side lengths?
Yeah,
Yep. What about HD and GC?
it's the same.
It's the same, exactly. The vector would also be the same, HD and GC, because it's going in the same direction, up north. So there we go. That's the answer. Yes, they are equivalent because the vectors, the component vectors, these are component vectors. They're equivalent in their dimensions. And that's that. Fairly simple. Oh. Oh no. Okay, here we go. This is a hard question. But I'll tell you this much. Even if we didn't know anything about vectors, the process of doing this is exactly the same. You can completely ignore all the arrows. We have two equations. How do we solve two equations? How do we solve this is a keyword now, system of linear equations? Remember that?
Mhm.
How do we do it? There's two ways. Substitution and what's the other one? Elimination, okay? To solve a system, of equations, you are either going to do substitution or elimination. So in this case, what would be easy? I always like doing elimination, I'll be honest with you, because I like crossing things out. So I'm going to do elimination. To do elimination, one of the coefficients, either the x's or y, they have to be the same. I want to make x's the same. What do I multiply equation 2 by? I want the coefficient of x's to be the same. This one has a coefficient of 2. What should we multiply equation 2 by so that they have the same coefficients?
-2.
Just 2. Then we can add them up. Yeah, if you do -2, you'd have to subtract them. I'm just going to multiply it by 2. So multiply that by 2, which gives us -2x plus 10y. You have to do it throughout. That is equals to 12b. Do we add or subtract to cancel out the x's? You add, right?
Mhm.
So you get 13y is equals to a plus 12b, which means y is a plus 12b over 13. There we go. So that is y in terms of a and b. What about x? How do we solve for x in terms of a and b? You plug that y back into any of the equations. Once you have one of your unknowns, you can plug that back into the equation to get the other one. So I'm going to replace this y over here. I'm going to do a substitution. You have to do it to find the other variable once you have one variable. So I'm going to replace this y with this. Actually, let's clean this out first. Let's move the x here so x becomes positive. So x is equals to 5y minus 6b, like that. I move the x on the right, move this on the left, like that. Now we want our answer to be in terms of a and b, so we're not going to touch this. But we don't want y in our answer. So what do we do with this y? We do a substitution, yeah?
Mhm.
We replace it with this. So that y there, so it'll be 5 times a plus 12b over 13 minus 6b, like that. Does the 13 multiply into the 5? Or only the numerator multiplies into the 5? It's only the numerator, okay?
Mhm.
Because this one right now has an invisible denominator of 1, so it's only the numerator that multiplies into the 5. So then this becomes 5a plus 6tb over 13 minus, now the LCD here is 13. This was an invisible denominator of 1. So we multiply this by 13, multiply this by 13, that'll be 78b. 13, like that. The final answer is x is 5a minus 18b over 13. That's my x, and my y was this thing that we found earlier, and that's the final answer. So it's just a elimination substitution problem, grade 10, okay?
Mhm.
The vectors just, yeah, you can do the same thing with vectors. That's the main point. The next question might be more difficult. All right. So now we need to prove that A is 1/3 of B, right? A is 1/3 of B. So how do we do this? All right, let's look at what's given here. We have X, Y, and Z. Let's solve for either X or Y. Where do we start? We can start anywhere, but not everything is going to help us. I'm going to start right here. A is the vector X minus the vector y. Yeah? Now that is from our second equation. What is y equals to from our third equation? If I want to isolate for y, what would that be?
It's b plus z.
Y is b plus z. That's right. So that's from our second equation. I'm going to use this. I'm going to replace y with that. So now we have a in terms of x, b, and z, right? But we don't want it in terms of x and z. So let's play with this. I'm going to multiply both sides of this equation by 3. So I get 3x is equals to 2y plus z. Let's see if that helps us. So I'm going to rewrite this as x minus b, yeah? Plus z or minus z? If I replace this y with this,
It's plus.
no, it'll be minus because there's a minus sign in front of it. So both of these will become minus. So we have x minus b minus z. Good?
Mhm.
Now what? Now let's replace z with what it actually is. So z is x. I'm just going to do this. So z is 3x minus 2y. So we have x minus b minus 3x. Does the y become positive or negative? If I replace this here, y will become positive, yeah? Like that.
Mhm.
So now what do we have? 3x plus 2y. So x minus 3x, that's negative 2x minus b plus 2y. Did that help us? Yeah, it did. Yeah, it did. So now negative 2x plus 2y minus b, yeah? If I take a negative 2 out, what am I left with? Between these two, if I take a negative 2 out, what am I left with?
X minus y.
Exactly, x minus y. Do we have an expression for x minus y? What's x minus y equals to? A, right?
A. Mhm.
So we can rewrite this as negative 2a minus b. That's not the answer, there's one more step. So let's just recap what we have. We have vector A is equals to negative 2 vector A minus b. You see it now, how we can get this? What do we do? Just one more step. What do we do on both sides? You want to group up the like terms. It'll be 3a. Move this here. 3a, like that, equals to negative b. Now what do we do to get the final answer?
You divide by 3.
Boom, done. And there we go. So this one was definitely tricky. It looks pretty easy, but it's not, because you have to do a bunch of substitutions and you want to make sure you don't do a double substitution of the same thing. If you do that, then you would end up in a circle, in a loop, in a never-ending loop, okay? Only do substitutions once, and once the expression is used up, just throw it away. So this one was definitely tricky. Maybe try this by yourself, see if you get the same answers. And again, there's, like we said, vectors, commutative, associative. There's multiple ways to do this. This is just one of the paths I took. You can probably start here and get that. Okay, let's try doing something a little bit more interesting. What's a trapezoid? Something like this. T, X, nah, it's the other way around. T, X, so they have to be going in the same direction. So maybe this way. Tx, zy. Cool? Because it says tx is twice as zy in the same direction, so that's why. Tx, yz, that makes sense. So now we have diagonals. So let's say we have this diagonal, we have this diagonal, and that is the point O. Find an expression for TO in terms of TX and TZ. So we can only have the answer in terms of this and this, okay? Any ideas on how to start? We want this vector TO, okay? We want this vector in terms of TZ and TX. Think about it this way. This is TZ, and you can move vectors around. What happens if I move TX up here? You would get this vector, right?
Mhm.
Is that what the question is asking us? Is that TO? So this one was TZ. And this one is TX. So if I move this vector up there, that will not be TO, right? That'll be the bigger one.
Mhm.
But we know that one side is half as big as the other. So that means to get this vector, you just have to half TX. There we go. That's the answer. And that's the end of the question as well. So again, some of these are tricky, and that's why we've been trying to visualize a lot of it, because not everything you can do it algebraically. You have to be able to see it. Sometimes that's the only way, which is a skill in and of itself. If you can see it, then everything becomes super easier. Like right here, AG and BH, are they equivalent? AG is going this way, BH is going this way. If this is a rectangular prism, they would be equivalent, okay? Because the only way you can go from here to here is if you go right, up, sideways. Same thing here. You need to go both length, width, and height across to go from one vertex to the other. So these two are probably the same because the dimensions are the same. The vectors, though, no way. The vectors are going the wrong way, but the dimensions are the same. All right, let's call it there for today.
Okay, thank you.
See ya.